If I have an orange and I go on a slicing streak, eventually I will reach a point where I cannot cut the orange any further. There is a limit to how small you can cut an orange. It cannot be divided into infinitely small pieces. It is made up of a teeny tiny indivisible thing. That thing is called an atom. And it's not just this orange that's made of atoms. Even I am made of atoms. Even you are. All stuff in the universe is made of atoms. The story of how we landed to this fact is long and awesome, and we will look at it later. There are trillions and trillions and trillions of atoms in this minuscule orange slice, and they are all indivisible. Just kidding, they're not. Atoms are not indivisible. They have a substructure. Atoms themselves are composed of 3 constituent particles that are much smaller: protons, neutrons, and electrons. The protons and neutrons are densely packed together in the center of the atom. They form the nucleus, whereas the electron orbits around the nucleus. There are different kinds of atoms, not just ones with 2 protons, 2 neutrons, and 2 electrons, as shown here. You can have 2 protons, 3, 4, 5, and so on. In every atom, the proton to electron ratio is always the same, 1 to 1. The protons and electrons come in equal numbers. We don't care about the neutrons right now. This visualization of the insides of an atom are, well, they're cool, but unfortunately they're wrong, because they do not take into account several things that we will look at sometime later. But for our purposes, despite how inaccurate this model is, or idealized this model is, it's a sufficient picture. Protons and electrons are charged particles. They have what we call electric charge. Protons have an electric charge of +1, whereas electrons have an electric charge of -1. Neutrons are, well, they're neutral, hence why we do not care about them. So, what exactly is electric charge? Well, it's a property. Just like how these protons and electrons have mass, they can also have charge. Like charges repel, and unlike charges attract. A proton will repel another proton because they both have a charge of +1. And an electron will repel another electron because they both have a charge of -1. However, unlike charges repel, so a proton and an electron will attract each other because of their unlike or opposite charge. This is why the electron orbits around the proton in a simple hydrogen atom. Since atoms are composed of an equal number of positive protons and negative electrons, we say that they are electrically neutral because the positives and negatives cancel one another out. However, that is not always the case. Objects can exchange electrons when they, for example, rub against one another. You and a ruler, both are for now neutral, as the number of positive and negative charges are equal. You take the ruler and rub it against your hair. As you do this, the atoms in your hair are losing electrons. The electrons are jumping onto the atoms of the ruler. Since the ruler has now gained negative electrons, it has a net negative charge. On the other hand, since your hair has lost negative electrons, it has now gained a net positive charge. The two are now charged and attract each other. You may have done this before with a balloon. What we see here is a phenomenon called static electricity. When you have a charge imbalance that needs to be returned to equilibrium, boom, that's static electricity. Static electricity is also what governs lightning. Charge is a property of objects, yet we sometimes call charged objects charges. That's because we are lazy creatures. Since like charges repel and opposite charges attract, we know that there will be a force at play when charges interact. If I place a positively charged object near a negatively charged object, they both will be pulling on one another, causing the attraction. And when I have two like charges, they will be pushing on one another, hence causing repulsion. The force in both cases will be measured in newtons, and that force will cause acceleration because F equals ma. And just like how we learned to calculate the attractive gravitational force between two objects using Newton's law of gravity, we can calculate the exact attractive or repulsive electric force between two objects using Coulombs law of electricity. The law tells us that the magnitude of the electric force between two charges increases with the amount of charge and decreases with the distance between the charges. Or mathematically speaking, F equals K Q1 Q2 divided by R squared. This law was formally formulated by
Charles Augustin de Coulomb.
the force between two charges is equal to the product of the charges times a constant, Coulomb's constant, divided by the distance between them squared. This equation looks suspiciously similar to that of Newton's law of gravitation. They both calculate a force between two objects. They have their specific constants, they multiply specific properties of the objects, mass and charge, and the product is divided by the r squared. However, there is a conspicuous difference between the two. The electric force between two objects can be both attractive and repulsive, depending on the charges, whilst the gravitational force is only ever attractive. That is why here the value for F can be both positive and negative. If we get a positive value, it is a repulsive force, whereas if we get a negative value, we are dealing with an attractive force. Let us play around with this law and calculate the electric force between two oppositely charged ball-shaped objects, A and B. A has a charge of 1 and B has a charge of 1. What are the units of their charge? Well, charge is measured in coulombs. The distance separating A and B is 0.01 meters. The value for Coulomb's constant, K, is 9 times 10 to the power 9 Newton meters squared over coulombs squared. Plugging in the values into the equation, we see that the repulsive electric force between them is equal to 9 times 10 to the power 13 newtons. That is a ridiculously large force. They are running away from each other big time. But wait, because they have mass, won't these two objects also be attracted gravitationally while being repelled? Yup, and we can calculate that with Newton. The two both have a mass of 1 kilogram, and plugging in the values, we see that the gravitational force between them is 6.67408 times 10 to the power minus 7. Yeah, they're being attracted all right. The electric force is much, much stronger than the gravitational force. Coulomb has got bigger muscles than Newton. Positive and negative charges display opposite behaviors. Hence why we call them positive and negative. But we could have also called them black and white, up and down, or foot and hand. It doesn't matter, for it is just a convenient label. The law of conservation of charge tells us that the amount of charge in a system will remain the same with time. There is another appreciable similarity between the gravitational and electric force. Newton showed the world that he could predict the motion of the moon around the earth and the planets around the sun after he propounded his theory of gravity. But it's really weird that a giant ball can exert a force on another ball through space without even touching it. Me, when I want to apply a force on something, I push or pull it. And that's the case for you too, I think. But how does the Earth impart a force on the moon? That's like a very long distance away from it. That's just what people were wondering. And sadly, Newton had no answer to this conundrum. And so is the case for the electric force. How does a proton pull on an electron to keep it in orbit in an atom? across a distance. In the 19th century, a great guy named Michael Faraday would give us an answer. Let us say we have a charge of 1 coulomb in empty space, called Z. This charge, according to Faraday, is creating a field around it. In physics, a field is a set of values assigned to every point in space. This is a vector field, where each value is denoted not as a number, but as a vector. The field strength weakens as you move further from the charge and strengthens when you do the opposite. Right now, there is no force being exerted anywhere. However, if we bring in a small test charge with an infinitesimal positive charge, one that cannot really affect our original Z, and place it at this point X, we will see that the charge is pushed away because of the positive-positive repulsion. The electric field surrounding our original charge is what mediated that force. It caused that force. Although this might seem like an ineffective explanation, it has virtues. The electric field at point X, where the test charge was, can be called E. And E is equal to the force experienced by the test charge divided by the magnitude of the test charge. E equals F over Q. The electric force propagates because of the electric field, just as the gravitational force propagates because of the gravitational field. None of these fields are actual things, they're just mathematical conveniences that work in describing the universe. The force experienced by our test charge is not constant at every point in space. Here it is greater than as compared to here. This is because the strength of the electric field increases the closer we are to Z. I like to think of the electric field as the sphere of influence of a charge. Okay, so the electric force is cool, alright, but you know what's even more cool than the electric force? Electricity. With the mere flick of a switch, I get a constant source of light at home. With the mere flick of a switch, I can power up a device that allows me to watch the Unreal Junkyard videos at home constantly. How? What is electricity? The word electric is present in electricity, so it's unsurprising that what we've learned about the electric force is related to electricity. Take this wire. It's made of copper, which is a metal. And because it's a metallic substance, the electrons in it can jump from atom to atom. This means that electrical charges, electrons, can flow through this wire. The charges in this wire, the electrons, are flowing from left to right. That's the electric current. And with these electrons are flowing their individual electric fields. These fields are moving with the electrons. But the electric field is not the only field here in question. There is also another type of field. Hi, thank you for watching this video. If you feel certain explanations weren't understandable or you have any questions related to them, please write to me in the comments section or through Gmail. If you'd like to know which resources have been used to research and create this video, I've linked a document containing them underneath. I've also linked a short worksheet that you can solve to test your understanding of this topic. Goodbye.